Throughout time, humans have gathered knowledge and inspiration from nature's library. As the interdisciplinary field of biomimicry explodes, it is becoming the standard for the development of new, groundbreaking, societally impactful technologies of the future. Finding inspiration in the world around us, we have turned our eyes in curiosity to the Australian thorny devil and Texas horned lizard for their peculiar water processing and distribution abilities. Findings published in 2007 by Sherbrooke, Scardino, Denies, and Schwarzkopf duly noted and described these creatures' innate abilities to rapidly move water through the interscalar spaces on their skin's surface. Though different species, both these desert lizards share the similar aptitude for the transport of water. Their skin's capacity to effectively and efficiently transport water is due to the semi-tubular channel system of hinge joints that water is transferred. The complex topography of the fractured surfaces and scale-hinged basally expanded and semi-enclosed channels formed by the hinge joint connections with the scale hinges on the body contribute to this phenomena. The hinge joint channels and spaces between scales or scale hinges are the key component in understanding the lizard's water channeling abilities. Following suit from the biological discovery of the natural design of the lizard's skin, we have extracted the most important principles in order to make a water collecting filtration system or water panel that runs on low energy input that is based off the same forces that initiate water flow in these desert lizards.
Prior to the 2007 findings that we studied, relatively little was known about the morphology of the lizard scales, nor about the physical mechanisms of water transport. It was believed that interscalar capillary forces were sufficient for cutaneous water movement, and that such forces were powerful enough to even allow the thorny devil to remove water from the damp sand via its ventral scales. However, as the researchers soon discovered, this was only part of the whole picture.
The researchers' methods were quite simple. Remove pieces of skin from the lizard, stain them, and observe their microscopic structure via scanning electron microscopes. More specifically, they wanted to look at the inner surfaces of the beta-keratin layer of the epidermis, focusing on the relatively uniform scales found on the lizard's ventral side. Additionally, they examined the buccal structures in the lizard to understand drinking behaviors. They found that the hinge joints, expanded regions underneath the more superficial scale hinges, formed an enclosed semi-tubular channel network with diameter approximately 100 to 150 microns, whereas related non-transporting lizards had more open hinge joints and thus did not exhibit the semi-tubular channels. The essential features for cutaneous water transport are as follows. First, interscalar spaces that are deep and narrow enough to partially close off an expanded semi-tubular network of interconnected hinge joints. Second, convoluted features of hinge joint walls that greatly increase internal surface area of semi-tubular network. Third, modification of scales and integumental structures at rear of jaws along with buccal action that facilitate movement of water in network.
Facilitated by a surface covering called Oberhaupten, which helps bring in water from the scale hinges, capillary action in the hinge joint channels work well until they are saturated, at which point negative pressure generated by drinking movements of the jaw and tongue comes into play. These mechanisms work hand in hand to allow the thorny devil and the Texas horned lizard to live in even the most arid environments.
The foundation of our design hinges on the ability of our water panels to collect water efficiently. That's our function. The microscopic layout of each individual panel will make us use of the same capillary forces that drive cutaneous water transfer in the desert lizards, as you can see here. While an external pump leading from the primary underground reservoir will emulate the negative pressure generated by drinking in the lizard. There will also be a strong similarity between the environment of our water panels and the environment of the thorny devil lizard, the Australian outback. Arid or semi-arid regions with sporadic rainfall. The primary concern for us is scaling.
So on average, an adult thorny devil lizard is about 20 centimeters long and weighs about 100 grams. At any one time, the amount of water in the hinge joint channels is about 3.7% of its body mass, or about 3.7 milliliters. So this is the amount that will be stored in the capillary network at any one time. So keep in mind that water will be flowing through this at all points. While this might be sufficient for the lizard's purposes, it may not necessarily fulfill the needs of an entire community of humans. And to this end, our water panels should extend as much of a region as possible. And so if you see over here, you can see that we're just trying to make this region as large as possible to almost have like a plantation of water, essentially. But this may end up increasing the cost of our overall area of land needed to make these water panels, and so more research is needed to see just how much we need to.
Here we have created our design model that consists of 2 panels, of which are comprised of small-scale structures mimicking the skin of the desert lizards. Our design is formatted with spaces in between the scales to display the semi-tubular hinge joint channels with convoluted walls. An important concept to recognize in the lizard's functionings is the negative pressure that is generated at the head and in the mouth by jaw and tongue movements that helps generate water flow on the lizards. To account for the additional forces that contribute to the generation of the flow of water, our model is created so that each panel is constructed at a slight incline to direct the flow of water to a mouth of a collection system that then drains into a collection well underground to later be pumped. This incline will create the negative pressure that facilitates movement of new rainwater into scale hinges. Each panel will be double-sided to ensure optimal efficiency from absorbing water held in the sand and from water absorbed from drastic temperature changes overnight that generate an excess in dew and moisture in the air that can be collected from through the capillary systems of the panels. Optimally, there will be multiple panels across a large area of land for water collection. Each panel will then be extracted from, and the water from all the panels will be directed into one collection source well underground.
As for following up on our trial design, we plan to collaborate with the UNICEF TAP project, a nationwide campaign that provides clean water and adequate sanitation to children around the world. Currently, UNICEF works in more than 100 countries around the world to improve access to safe water and sanitation facilities in schools and communities. Considering our water panel's low energy input and high efficiency, UNICEF would benefit from using our water system to serve impoverished villages. One critical information we do need to proceed with this project is the feasibility of artificially constructed interstellar surfaces that emulate the thorny devils. It would cost a lot of money to initially build the microscopic hinge joints and the semi-tubular networks for many panels in order to get enough water to serve a whole village.
More than 884 million people in the world lack proper access to safe water supplies, and by 2025, 1.8 billion people will be living in countries or regions with absolute water scarcity. Considering these startling facts, there is exciting potential to create a water collection and filtration system for arid and water-lacking areas based on our product's ability to gather water from the rain, soil moisture, and water molecules in the air using principles of gravity to create a low-energy water collection system. The grooves of each cell on the water panels will allow for dew to condense on them and be drawn in by capillary forces. To combat the reality of today's water shortages and lack of access to water, our water collection panels will help alleviate some of the strains on developing countries that so often limit its people to fulfill their potential. The implementation of this technology will societally create environments in which people who would normally be forced to spend several hours of their day collecting water from distant sources will be alleviated of this burden. When basic necessities such as access to water is alleviated, society as a whole benefits because people are given the ability to focus their time and attention towards other things such as education. The economic efficiency and the low energy input requirement are also an advantageous concept of the construction of these water panels. While societally necessary and impactful, these water panels can be implemented worldwide as a new form of water collection and distribution.